Good.
Hello, hello, good evening, and welcome to another Science Cafe in the Shining a Light on Chemistry series. For those of you who've been coming to this series before, I'm happy that we have warmer weather this evening, and we're entering into that sweet spot in Tucson. And it's a little bit lighter out this evening at this time of day than it was last month, and that's why we tried to rig up the shade structure, and we moved the projector a little bit closer, and the light will continue to fade, but hopefully you'll be able to make out what's on the screen because it's fascinating. And I'm excited for the presentation, but I'm also going to give a quick plug for the College of Science Outreach Sites. My name is Shepard Reed. I work at Flandreau Science Center and Planetarium. We have a new full dome show about exoplanets called Undiscovered Worlds. How many people have heard of exoplanets? Wow, we are an informed audience because I've asked that a few other times and like one or two hands go up. But if you haven't heard of exoplanets, they are planets that are orbiting other stars, not our sun. They are planets outside of our solar system. And within about the past decade, we've realized that we've actually identified thousands of them. And if you extrapolate that out, that means there are millions of other planets orbiting other stars out there. So it's a fascinating new field of science. It's a really cool planetarium show. And to highlight that planetarium show, we've put together a speaker series once a month at Flandreau in the Planetarium Theater, because there are so many researchers at University of Arizona that are working on different aspects of exoplanet research. So if you go to the Flandreau website, you'll be able to see that. And of course, the other College of Outreach science sites, College of Science Outreach sites, got that a little jumbled, are the Mirror Lab, the Tree Ring Lab, Biosphere 2, Tumamoc Hill, and I feel like I'm forgetting one, but that's enough. So thanks for being here tonight. We're very pleased to have Mark Burton. He's another PhD candidate in the Department of Chemistry and Biochemistry. And tonight we're going to hear about how we can use microwaves to probe the chemistry of space. I got to preview this presentation. It is absolutely fascinating. Can we have a big round of applause for Mark Burton?
All right, so thank you everyone for coming to the third installment of this series, Shining a Light on Chemistry. As you can see, the light is against us here, and my entire talk is going to be about how light is good for us, but this is one of the examples where light is actually bad for us. So as you can guess from my title here, I'm going to be discussing how we can use microwaves to determine the chemistry throughout space. And this phrase, chemistry throughout space, may be a little unsettling for yourselves because we mainly think of space as being this vast emptiness with nothing in it. And although that's true, space is a vacuum, there is still plenty of molecules that exist on it. To give you an example of this, it may be hard to see, but we have what we call a planetary nebula. It's my background there. And in the center of that nebula, we have a dead white dwarf star. And this star is emitting a lot of this very strong radiation, a very strong light. And so early astronomers prior to the 1950s thought that no molecules can exist there, that radiation will just blow all the molecules apart. But what we've shown over the years is that this entire cloud is has an abundance of molecules, different species, radicals, things that we won't see here on Earth. So what I'm going to be doing today is going through what is known as stellar evolution, where we have a star, how it dies, what happens with the material that the star produces, how new stars are formed, and from those stars, how we get solar systems. The big question here is, when we make the solar system from these dead and coming back to life stars, when we get planets like Earth, how do we get the complex chemistry that we see here, such as DNA or sugars, so on and so forth? These molecules are so complex that you won't see them out in space, but the material to make them has to come from somewhere. I.e., does that material come from comets, meteorites that crash onto Earth, or is that material already present when the Earth forms? So this whole series is about light, so that begs the question, what is light and how can we use it? Well, one of the most important reasons is it helps us see. For instance, in 2006, in the Cassini mission, light allowed us to see these extremely high-resolution images of Saturn's rings. There are many more rings than they previously thought because we were never able to get this close to Saturn and collect these beautiful images. Furthermore, with that, closer to today's date, in 2015, was the New Horizons mission, where they collected this image of Pluto, in which they've never been able to get this beautiful photo of Pluto before. And what they saw is that the surface of Pluto is heavily cratered, meaning that a lot of things must have bombarded this surface through many, many years. We can also use light in other ways other than just seeing. For instance, we can use light as an energy source to send these machines to systems. For instance, in 2014 with the Rosetta mission, the scientists sent a rover. You can't see it right here, but there's a little rover that they sent to an asteroid. And then when that instrument sat down, it started collecting the samples. So we can use light as an energy source. And to give you an idea of what's to come, this is the Osiris-Rex mission is a mission that NASA, it's a NASA mission led actually by the University of Arizona, where they're going to send a spacecraft using solar cells as the light capturing device. So again, light is energy. Send it to an asteroid, physically collect samples, and bring them back to Earth, something that's never been done before. So there are a multitude of ways that we can use light, either seeing it or using it as an energy source. But what about something that is so far away that we can't send something to? Something like the Red Spider Nebula that I showed on the front slide. To give you an example of what I'm talking about here is magpies. It is about 70 feet long from where I'm standing all the way to the people in back. Shout out to magpies. The length of the university is 57 magpies. It's not too far from Campbell all the way down to Park. If you extend that a little bit more, the length of the United States is 120,000 magpies, so a lot of water. Something like Pluto, the farthest that we've sent a spacecraft is 350 gigamagpies. That is 350 and then 9 zeros after that, so that's a huge difference, a huge distance. Something like the Red Spider that I showed you earlier is over 93 examagpies. That is 93 and then 18 zeros after that. There is no way that we have the technology to send a probe to it. So we have to rely on the light coming from that source in order to learn something about it. Now when I say light, a lot of people think of this right here, the visible spectrum, what we can see with our eyes. However, I'm here to tell you that that visible spectrum is only a small portion of what we call the electromagnetic spectrums. And the spectrum ranges all the way down from radio waves all the way up to gamma rays. And there are certain ways that we can classify these different regions in the electromagnetic spectrum, one of which is the wavelength, where it is the bottom of the wave to the other bottom of the wave, or the top of the wave to the other top of the wave. And as you can see here, radio waves have very long wavelengths, whereas gamma rays have very short wavelengths. And if we relate it to this equation here, that means that radio waves are very low energy, whereas gamma rays are extremely powerful sources of light. And even though you may not realize that this is light, we interact with all forms of this radiation in our daily lives. For instance, radio waves in cell towers, if you listen to the radio in your car. Microwaves, we have one in our homes, it helps heat our food. If we go up in higher in energy to infrared radiation, that is something like a heat camera or heat sensor. Even higher in energy with ultraviolet. For those less fortunate to live in the desert, they need tanning beds. And if you go even higher to X-rays, we can image our bodies with it, in which the last series back in February talked about. Now, because of my field, the field of astrochemistry, studying space with chemistry, we use different terminology. So instead of wavelength, we talk about things in frequency. And just so you know, they are opposite of each other. So very short wavelengths have very high frequencies, and very long wavelengths have very low frequencies. So if you hear me say frequency, it's just related back to the wavelength of light. Okay, so we can go from these very macroscopic large things and see how light is interacting with very small things, i.e. molecules. Just a refresher, a molecule is just two atoms bound together. Could be oxygen that we're breathing, the water that we drink, or the amino acids inside our body. They're all molecules. A simple case of it is going to be two atoms where it's a nucleus and some electrons, and those electrons are being shared between these atoms in that molecule. So when we shine light onto a molecule, what happens is that that light has a certain energy, and if that energy matches the energy gap within the molecule will absorb that light. An analogy to this would be if you wake up in the morning and you're very groggy, you're very tired, but then as soon as you drink some coffee, you're in a higher energy state. The same thing is with a molecule. It just needs that initial pump of coffee. But much like coffee, you get to noon, you start running low again. Same thing with molecules. They don't like being in that highly excited state, so they relax back down to a lower energy state and emit that same wavelength of light. However, depending on the wavelength of light that we shine on this molecule, it'll interact with the molecule differently. For example, if we shine microwaves onto a molecule, it'll cause the molecule to rotate. Interestingly, this is why microwaves work. It physically rotates the water molecules in your food, causing it to heat up. If you shine infrared radiation on it, it makes the molecules vibrate. It gives them a little groovy music to dance to. If you go higher in energy to visible or ultraviolet, this light can physically rearrange the electrons within the molecule. And if you go even higher in energy to X-rays, this is enough energy to physically eject the electrons away from the system. And so, as you guessed from my title slide, I'm going to be focusing on this very low energy form of radiation, microwaves. Now, why do we need to use microwaves in order to study space? Well, there are actually a multitude of reasons. One of which is that microwaves yield molecular specificity, meaning that when you shine microwaves on something, it rotates, and as it rotates, it has a moment of inertia. And that inertia is directly related to how massive it is, as well as the length inside of it. So for instance, my hand to my shoulder versus my hand to my shoulder now. It's a different length. And with the Winter Olympics right behind us, I thought this was appropriate, where the skier, as she's rotating, she's moving her leg closer to her body, so she's changing the length inside of her system, and she's spinning at a different speed. The same thing happens in molecules. So right here, I have two different molecules, HCP and HCN. The only difference is that one is right above or below each other on the periodic table. But because phosphorus is heavier, it's more massive, and the bond lengths within these two molecules are different, they will rotate differently. Possibly. They should. Oh, it's trying to connect to Wi-Fi. I said they will rotate. Rotate, there we go. They will rotate differently. The more heavier molecule, thank you. The more heavier molecule will rotate slower than the lighter one. And it's because of this property that their masses are different, their inertia are different, they will rotate differently. Molecules are a great, microwaves are a great way to distinguish between them. This is also very important when we have much larger molecules, but still very similar. So here are two different molecules. The only difference is this group right here. This is a CH3 group versus just an H, a hydrogen. If we were to shine UV or visible light on it and try and rearrange the electrons within the molecule, it may be hard to see how these electrons are changing from these electrons. Similarly, if we shine infrared light and try and make it dance a little bit by vibrating, it may be hard to see how this bond is vibrating versus this one. But as soon as we shine microwaves on it, they're going to rotate differently, therefore we can definitely tell them apart. So microwaves are good. It gives us a way to know which molecules which. Another reason is because collisions happen frequently in space. So right here, I have an image of a circumstellar envelope around what's called an AGB star. I'll go into that later, called IRC plus 10 to 1/6. So here we have our two molecules. They're floating through space, minding their own business, but then they're going to come together eventually, collide with each other, and start to rotate. And when they rotate, they're going to be emitting that frequency. So in our energy level diagram here, what happens is that collision is enough energy to excite them rotationally. What this means is that we don't need that initial input of light. We don't need that coffee to make them excited anymore. It just happens with these collisions. So after they collide, they're excited, and then after time, they're going to relax back down and emit that wavelength of light. So even right now, molecules are rotating in space, colliding with each other, and then bombarding you with the frequencies that they are emitting. Yeah, don't be scared. A third reason why we should use microwaves is because the sun is a problem. As you'll hear in the next month's talk of this series, the sun is emitting a lot of ultraviolet and infrared radiation. So if we're trying to look for these types of wavelengths coming from space, it would be hard to see what's coming from space and what's coming from the sun. So, as a result of this, these electronic and vibrational motions with this ultraviolet and infrared radiation can only be detected at night, whereas these microwaves, these rotations, can be seen 24/7. So my boss is very happy about that because I can work 24/7. Now, I keep using this word detected light, seeing this light, but how do we actually do it? Well, it's not as simple as just importing a huge microwave into space and then putting a star in the middle there. That's just not possible. So we have to rely on telescopes, specifically radio telescopes for microwave spectroscopy, microwave observations. There are numerous telescopes around the world. There are 2 here in Arizona, the sub-millimeter telescope on Mount Graham, as well as the 12-meter telescope on Kitt Peak. However, something fundamental of these telescopes, the larger the dish that you have, the larger this primary dish is, the better information you can gain from these sources. So as you go from this 12-meter telescope to something like the IRAM 30-meter telescope in Spain, you can gain a lot more information. One even better than this IRAM telescope is a new one, recently new, within the past 10 years, called ALMA, or the Atacama Large Millimeter Array in Chile. And what they do is that they take a whole bunch of these 12-meter telescopes and link them together. And so effectively what they have here is a 10-mile-long telescope. Now this thing is a beast. It's been able to pull out information that we could never do with these smaller telescopes. So what happens when we're trying to learn something about space is that, let's say we wanted to learn something about this very oxygen-rich hypergiant star called VY Canis Majoris. We shine our telescopes at this source. It is constantly emitting this radiation. The collisions are happening. And so all of this radiation is going to be collected from this dish, reflect off this main dish here, go to what's called a subreflector, and then through a very small hole in the dish. And from there, we can analyze the data. And there are many ways that we can analyze this data, one of which, if you look up here, is the Helix Nebula. And what they did for this source is that they wanted to study one molecule. One molecule, we know how it rotates, we know what frequency of light it rotates at, so we're going to sit our telescope to collect at that one frequency. And we're going to map that source, basically put the telescope here, then put the telescope here, put the telescope there, so on and so forth, and see how much of that molecule exists in that source. This graph, this picture is like a topographical map, like a landscaping map, where the lines very close together means a high density, farther apart, low density. So as an example, this region right here is extremely dense in that molecule. Down here, not so much. Over here, a little bit more dense as well. But then in the center, it's extremely barren. And so this is what those earlier astronomers were thinking, that these planetary nebula with that white dwarf star emitting a lot of that strong radiation will blow all the molecules apart. And partially they're right. There is no molecules in the center of the star, this nebula. However, as you move farther away from that center of that star, from that white dwarf star, we're seeing molecular material. Another thing that we can do, instead of sitting on one frequency looking for one molecule, we can scan over a large range of frequencies looking for any molecules that will come out. For instance, this is this bottom picture here of IRC plus 10/16, that circumstellar envelope that I showed you earlier. If there were no molecules there, you would see a flat line. However, we're seeing peaks everywhere in the source, indicating that there are molecules present in this source. So instead of looking for one molecule, we can search different frequencies to see what exists out there. However, in order to know that this peak here corresponds to that molecule, we have to make lab-based measurements, and this is where the chemistry and astrochemistry comes from. And the way we do that is actually quite simply. We put it in a microwave and shine light on it. That's basically it. It's real science, so we have to be very scientific about it. So this is just a general schematic of how they can do it. This is just a cell. It might have mirrors in it, who knows. And then some chemistry has to happen. There are multiple ways to make molecules. For instance, we can use a laser to ablate or blow apart material. So right here, I have a potassium rod, pure potassium in the middle. And you might be able to see the grooves in it where I've taken a laser and blown apart chunks of this material to get it into the gas phase. Another thing that we can do is physically heat it up. So if we wanted to study heavier metals, something like titanium or iron, we can heat it up in an oven until it reaches its melting point at a liquid state, and then get some vapor off of that and study it that way. And sometimes we can add what's called a discharge, which is just energy, which is why it looks blue there, for instance. And this energy just allows new molecules to form. Okay, so however the chemistry happens, we make some chemistries and we put it in there, and then we shine some light on it. Now, if this light, that energy of light, matches that of the energy difference with inside this molecule, the molecules will absorb it, rotate, and then relax back down and emit that frequency. So we'll collect these frequencies as they're being emitted. So what we'll see in the lab is something like this, where we input that frequency of light, didn't see anything, input that frequency, didn't see anything. But as soon as we input that one, we see a peak, meaning that that molecule absorbed that radiation. So this is what I mean by molecular specificity. We know that that peak corresponds to that molecule and no other molecule whatsoever. Something you should know, however, is that molecules can have more than one peak. Especially the more complex that molecule is, the more peaks it's going to have, making some of these observations and sources in space very difficult, just because there are a lot of lines that you have to look at. Okay, so now that I've gone through some of the astrochemistry aspect of how we see light coming from space, how we make molecules, I'm now going to go through the stellar evolution chart and talk about how the chemistry differs within all these sources. For your guidance, I have it up here circled of where we are so you can track the position of this evolution. I'm going to start with stellar evolution, basically with our star. So when a star is born, basically, it's very excited, very happy about getting $4 for their 4th birthday. And it might have a face like this. But as it grows up, it learns. It only gets better from there. And it can become something like our star, the sun, basically. And our star is on what's called the main sequence, or where this main sequence is still burning hydrogen. After time, however, the star will use up all of its hydrogen and become what's called a red giant star. And that's something like this one right here. It's a lot darker. Compared to where our star, our sun right now is, something of a red giant could be anywhere from 10 to 1,000 times larger, and the surface of it can be a lot cooler. Because it's so much bigger, it has to get cooler on the outside. So we can use these types of qualifications to see when a star becomes a red giant star. Another important thing is that when it reaches this red giant stage, it goes through what's called a dredge-up. And this dredge-up is important because it's mixing the material through the star. So anything that the star has made, element-wise, is going to mix through the bottom and then shoot out the star. So stars are constantly emitting the material that it's making. As the star goes on, it's going to go through what's called the triple alpha process, in which it's converting hydrogen to helium, helium into carbon, carbon into nitrogen, so on and so forth. That's where we get the elements. It's going to go through that process and then become what's called an asymptotic giant branch star, or an AGB star, I talked about before. And it's at this stage that the star undergoes this violent outburst where it's throwing all of its material away from it. That goes through another third dredge-up, we call it, and then it becomes what's called a planetary nebula. This planetary nebula is something that you've probably seen before. When people talk about space, they probably show you these types of images because they are absolutely gorgeous. So this is what I've talked about a lot of times thus far, where you have a white dwarf star in the middle of every one of these sources. It's emitting a lot of strong radiation. But because it just went through this stage of ejecting out all of this material, it forms what we call a circumstellar envelope, if you will, around this dead star. So this is where all of that molecular material is being seen. And depending on the initial star, if there's any outbursts from the star, it could have many shapes, like circular, spherical. It can have 2 lobes coming out of it. It can have 4 lobes coming out of it. It just depends on the source. So, as the earlier astronomers thought, no molecules can exist there. And I'm going to try and prove my point that they're wrong. So here's a graph. It may look confusing, but on this axis here, I have the abundance, basically how much of it you have. The higher you are, the more you have, the lower, the less of it you have. And on this axis here, I have the time, or the age of the source. And so what these earlier astronomers predicted is that with all of these triangles, the abundance of these molecules decrease with time, thinking that this white dwarf star is going to completely blow apart these molecules and nothing will be left over time. However, what observations over the years have shown in all these circles and stars is that the abundance of this material is staying constant. And what that tells us is that these molecules must be protected somehow inside this planetary nebula. One of the theories is that it's sometimes cold in space, you know, just very, very cold. And so these icy snowballs called grains or chondrules can form that can shield these molecules from being blown apart from this radiation. So that's one theory. It's being shielded from dust, basically. To give you an idea of the types of molecules that can form in these sources, in these nebulae, we're seeing ions, basically, where an electron has been ejected out. We've seen highly substituted species where isotopic substitutions, where a difference in a neutron, basically, very less abundant than its parent isotope. Even carbon chains, so 2 carbons, 3, 4, all the way up to 7. And then something as massive as what's called fullerene, which is C60. It's basically a soccer ball, and at each vertice is a carbon atom. So something as even large as this, it's still a small molecule, but something as large and complicated as 60 atoms can still survive this radiation field, basically. So what happens? This planetary nebula, the star dies and it's ejecting out all this material. As this nebula goes on, that material is still going away from that dead star. And so it forms what's called a diffuse cloud. We call it diffuse because you can definitely see the outline of something being there, some material, but it's light enough that you can still see the stars behind it. Now, as I mentioned earlier, collisions happen frequently in space. That's why we don't need that initial input of light to view these molecules rotating. However, in diffuse clouds, these molecules are so far apart that they're not colliding with each other. It's like me trying to collide with someone in the back. It's just not going to happen. So we weren't able to observe these types of sources for many, many years until one smart person came along and figured out how to do it. They went back to the basics and figured out, well, if this cloud isn't emitting the type of radiation that we need, we'll just have that input of radiation. So in order to view these diffuse clouds, we need a star behind it, basically. So instead of just seeing peaks coming from the source indicating molecules are rotating and colliding, we now need pure light behind it to basically pump up those molecules, to get them excited, to give them some coffee. And so what we see out is this weird looking spectrum right here, which is a combined image of those two. However, because so much more light can get into the center of this cloud, that means that the chemistry will be completely different. And that's shown in the molecules that we see. We're seeing a lot more of these ions, basically more light is ejecting those electrons away, and we're seeing a lot smaller species here, 2-3 atoms on average. And so just going from a star with a strong radiation field, but some of it being clumped and shielded, to this diffuse cloud, the chemistry can change drastically over 10,000 years. I know that doesn't seem like a lot, but in space, it's a lot. However, over time, these clouds, these molecules, will start gravitationally going towards each other to form what's called a dark cloud. And no, this is not the light interrupting it, it's just that dark, where this Barnard cloud, for instance, is obscuring all the light behind it because it's so densely packed with material, with gas phase molecules, these chondrules, these grains, dust, basically. And I grouped together these dense clouds and star formation regions because in these dense clouds, because they're so highly packed, new stars can form. There's so much material there that it's so energetic that a new star can form. And that's something like this image here, where you can kind of see the remnants of a dark cloud, but then a star forming right there. You actually have seen one of these practically all throughout your life in the Orion constellation. So here is the Orion's belt of the Orion's constellation. And the brightest star just south of that belt is called the Orion Nebula. Picture right here. You can see it's absolutely gorgeous, a lot of beautiful colors. And in this nebula is the starting of a dark cloud right in the center right here. So if I zoom in to just that right there, you'll see this image here. And this is an extremely well-studied source because of the unique chemistry that can occur there. Now, what you're seeing is in this image is actually quite cool in that from Earth, what we're seeing is the star first, and then this dense cloud behind it. However, on one side, this dense cloud is reaching in front of it. So we're getting both the back and the side view of it. So here is the dark cloud behind it, the star in the middle, but then right here is where that dense cloud is reaching in front of it. This creates what's called a photo-dominated region. We call it photo-dominated, photo meaning light, dominated meaning heavily happening. So photo-dominated because there's so much light happening. This photodominant region, called the Orion bar, has been well studied to see what molecules can occur in this one small region. And what we've seen is that right where the light is hitting the most, where that radiation from that star is hitting the most, we're seeing atoms, basically no molecular material. Those molecules have been blown apart. Mainly atomic oxygen, for instance, in this source. But as you move farther away, this cloud gets much colder. There isn't much light hitting it. They're not in a desert, so it gets colder, and larger molecules can form. We go from 2 atoms to 3 atoms as we move away. So even in one source, we can see drastically different molecules being formed just based on where it is. Another thing that can happen with these new stars coming into existence is that shock waves can occur. This shock wave is due to the excess energy that the star has just from being formed. You can think of this as being at the beach. You're in the water, the ocean's behind you, and you're standing like this trying to take a very pretty picture. However, a huge wave comes over and crashes over you. You get knocked down, your hair's a mess, it's dripping like crazy, your makeup's running, your bathroom's awry. The same thing happens with molecules. As this wave of energy comes over, it knocks them down and makes them into something completely different. They go from a beautiful person into a soaking wet beautiful person. And so because of this, both of these photo-dominated regions and this excess energy of waves, a lot of interesting molecules can form. To give you an example, in blue here, I've listed what we call organic functional groups, and they're just different ways of classifying molecules. And we're seeing a lot of different types. For instance, alcohols, like the ethanol in the beer that you're drinking right now. Amines, if you do any fertilizing or gardening, you probably use those, nitrogen-containing compounds. Carboxylic acids, acetic acid is in vinegar. Sugars, like the sweet, delicious chocolate that we all know and love. Sugars have been found in space, actually. And so with this huge range of molecules being formed, it's quite interesting because directly after the star formation region where all of these molecules have found is where we form planets. So right after this is what's called the protoplanetary disk phase. And what we have here, I have 2 images. We have that star that just formed and that dark cloud around it. Over time, angular momentum must be conserved, gravity starts pulling everything together, and it makes it into a disk. And this disk is very interesting because within this disk, the temperature can change drastically, hundreds and hundreds of degrees. Hundreds of degrees, I should say. So as before, the star is emitting a lot of strong light. It's hitting the outside of this disk. New chemistry can form, radicals can form, and just like inside the star itself, inside this disk, these molecules are being mixed all throughout this cloud. And as you go to the center of this disk, it gets much colder. So as that temperature changes, those molecules get locked into what they were. And in this cold region, these molecules start clumping together, and from that we get planets. So over time, all of this molecular material that was formed in these dense clouds and star formation regions will eventually become these rocky things that we call planets, and asteroids and comets and so forth. And so what you'll see over time is something like HL Tau, where we have a star in the middle, and then this is the previous dark cloud, dense cloud, and we start to see these small rings being formed where possibly planets are carving out the way of this material, start condensing down to these rocks. And you're like, I've got you. If dense clouds form solar systems, that must mean that a dense cloud is surrounding our solar system. And I'm here to tell you, there is. We normally don't talk about it. Here I have the inner workings of our solar system up to Mars, the asteroid belt, and then Jupiter. If you zoom out to the outskirts, the farthest planet, Pluto, if you still consider Pluto a planet, you have the Kuiper Belt. Interesting fact, this Kuiper Belt is named after the same person that the University of Arizona Kuiper Belt is named after. Right outside this belt is a planet called Sedna. It's a fake planet, I like to call it, because it's not really a planet that we consider to be part of our solar system. And that's because it has such a huge, irregular connection to our sun that we don't really care about it. But if you zoom out to just the orbit of this planet, to just this small thing here, you start to see what's called the Oort cloud. So pictured over here is the Oort cloud itself, and we're this tiny little dot in there. So it's of this Oort cloud that our solar system formed. All of that molecular material made our solar system and what we know today. Now we say that this cloud contains pristine material because it's what was originally there when our solar system formed. And we love studying these types of regions. However, it's extremely cold. There is no sun out there. It's not going to be heated. And so everything is condensed down onto these dirty snowballs, these rocks. And so we have to study them in an interesting way, i.e. comets. There are two types of comets, short or Kuiper Belt comets. An example of that is Helix comet. And those comets arise from this Kuiper Belt. These comets have very well-known trajectories. We know where they're going to be, when they're going to be. And so when they come in close to the sun and then go back out, what happens as they get closer is that the comet heats up. That dirty snowball heats up, the ice melts, and new molecules can form. It does this over and over again over the course of hundreds and hundreds of years. So we call this material very processed. It's heating up constantly and cooling again. However, these long type comets, for instance Hale-Bopp, come from this Oort cloud. Just to give you a scale here, a comet coming from this Oort cloud only comes by about every 700,000 years. And so we don't get to study that very often, but that means that that material is in process. It's pristine, perfect material from the start of our solar system. Now, what this means is that when these comets come close to Earth, we throw everything we have at them. We throw radio telescopes, infrared telescopes, optical telescopes, all at them to try and analyze as much data as we can while it's close to the sun. And there are multiple things that we can do. For instance, we can look at one comet and study it days at a time, day, wait, day, wait, day, wait, to see how the molecules are changing as it gets warmed up. And as you see here, there aren't many peaks here, but then there's a huge peak there and not a huge peak there. So this just shows that these molecular abundances, the amount of material that we have, is changing over time as it's passing through the sun. And just a reminder here, these peaks are indicative of molecules. We can even look at two different types of comets and compare how the material is different within them. For instance, in this top one here, you see a couple peaks over here, but not so much in the bottom one, meaning that these two comets could originate from somewhere else in our solar system. A fun fact about comets, actually, many people didn't know this, the tail of the comet isn't actually behind the comet as it's moving. It's not a comet's moving and the tail is this way. It's actually whatever direction is opposite of the sun. So in this picture, the sun is down here, the comet is moving this way, but the tail is opposite of the sun. A little fun fact for you. Okay, so as I mentioned, when these comets come close, we throw everything we have at them. And sometimes that means physical instruments we throw at them. I've talked about this before. It is the Rosetta mission studying Comet 67P, where they sent Rosetta instrument, Rosetta lander, Rosetta spacecraft to this comet and harpooned an instrument to the surface. So in this image here, this is right when the instrument landed down on the surface and it kicked up some of that material. And here you can actually see that instrument on the surface. So what happened is that this material got kicked up and the instrument started analyzing the data that is right here. It's very boring, I won't bore you. However, one of the interesting molecules that they found is this one right there called Methyl Isocyanate. Now this is an interesting one because it has never been seen before in space. So what we did, one of the postdocs at the University of Arizona did was use our radio telescopes here in Arizona to find this molecule in space. Where else is it? And so what they did, we are right here on our spiral galaxy. They pointed the telescopes right at the center of our galaxy to something called Sagittarius B2 North. It's a very dense cloud. It's a huge, dense cloud. So a lot of interesting molecules can form there. And what they found is this right here, where in red is where we're predicting that molecule to rotate. That frequency indicates that molecule. And in black is what we're actually seeing, and as you can see, it lines up perfectly. So we used physical data collected from a comet in tandem with radio telescope astronomical observations in tandem to learn something new about our galaxy and space in general. So in conclusion, there are an abundance of molecules out there, all different types. Where they're seen depends on the environment that they're in. Something that I haven't talked about, even metal-containing molecules have been seen in space. Even organic-like molecules, something like silicon, or silicone, which is in sand, or phosphorus, which is in our DNA, has also been seen out there. And this begs the question, what else is out there that we just haven't found? Can we see more complex sugars, something like glucose? Can we see phosphate, a main component in our DNA? Or something like alanine, which is an amino acid that make up the proteins in our body. Can those things exist in space? And if they do, where do they exist? Do they exist in a planetary nebula, where these molecules can be shielded by these dirty snowballs? Or do they exist in these dense clouds, where all these shock waves and photodominated regions can form these interesting molecules? Or are they made somewhere in the protoplanetary disk phase, with this new cycling of material and then just get stuck on a planet? Along with that, how will we find them? Do we need more things like ALMA, these beast of telescopes, these arrays, to actually get this information, this very weak information from these sources? With that, I would like to thank you all for sitting there listening to me babble on for a half an hour about a nerdy subject, as well as Shepard Reed and Aaron Deely, who set up this entire Science Cafe series. Without them, it wouldn't happen. And I'll take any questions you might have.